In this module, we would be discussing solids as crystals, or more specifically, crystalline description of solid. So, what do I mean by this? Until now, I've been describing solid as made up of ions or atoms and valence electrons. So, ions are heavy and immobile, and I've described this as arranged in a specific order, and valence electrons as being lighter and agile so they can move around, and depending on what kind of bonding is there within the solid, it can be delocalized within a whole solid, or it can only hop from one atom to another, given the nature of bonding which exists within the solid. Nevertheless, what we are interested in now is how would you describe this periodic arrangement of ions or atoms within a solid, and in how many different ways they can occur, and how would you mathematically describe them. This is a specific character of solid which is called as crystalline character or crystalline nature of solid, and this module is related to description of this crystalline nature of solid or crystalline arrangement of solids. These are the two readings from which I have taken most of this material. Um, if you look at solid in terms of this crystalline nature or crystallinity, you can classify solid into three main classes. The first and the first class is that of a single crystal. So you can think of a single crystalline solid as a solid in which the atomic arrangement is uniform throughout. So if you look, whether you look at the atomic arrangement within a small region, or whether you look at over the whole volume, either in the short range or in the large range, in both cases the arrangement looks exactly similar throughout the whole volume, and such a solid is called as a single crystal. Examples are the naturally occurring, there can be naturally occurring minerals or crystals which are single crystals throughout. One identification is that they can be cut nicely into these geometrical shapes. These are the two examples of borax and quartz crystal which are naturally occurring. These are not the only single crystalline solids which occurs, but you can also have artificially created or fabricated crystals as well. The other class of material in terms of crystallinities are polycrystalline material. So polycrystalline material are such materials which do have regions which are called as grains, such that there is specific arrangement within that grain and it's uniform throughout this grain. But if you go from one region of the solid to another region of the solid, the arrangement might change. It might be the orientation will change, or it may be the whole crystalline structure itself would change from one region to another. These regions are called as grain, and the boundaries between these grains are called as grain boundaries. But nevertheless, they do have, in a short range, they do have order, but over a whole solid, they may have different orders from one grain to another grain. These are called as polycrystalline solids. Some examples would be, for example, sand or metals. So this is an SEM or scanning electron microscope of aluminum, for example. So you can see that you have boundaries which define a grain, and inside the grain you have a specific arrangement of atoms, and if you go from one to another, it might be, the arrangement might be oriented in a different direction in such a metal. So these are called as they are called as polycrystalline solids. Then there are amorphous solids which neither have short range order nor have a long range order. And if you look at an example, would be, for example, silica glass, which consists of a silicon atom and two oxygen atoms, silicon dioxide basically. If you look at the arrangement, atomically they are not nicely arranged, so it lacks order at atomic scale, and same would be true for the whole solid. So these are the three main classes of crystal solid in terms of their crystallinity. One particular example which is interesting for single crystal is that of silicon single crystals. It's a single crystal which can be uh, fabricated in the labs. So, for example, this is one example. These are called as ingots, and the length may be a meter or more than a meter long, and this whole thing is a single crystal, which means that the whole solid has exactly the same arrangement. You can cut them into wafers, and you can make solar cells out of these wafers, or you can make integrated circuits out of these wafers, which are the chips which either in your mobile or in your laptop devices. So all of the information technology is basically based on these single crystals, technologically very important. So um, coming to the question now, how would we describe a crystal? And the important question to ask is, how can you mathematically describe a crystal? So before I go into that of a crystal, describe a very important concept related to crystal, which are called as Bravais lattices. It's a mathematical construct, and is the definition of the Bravais lattice. So a Bravais lattice is basically consist of is a collection of points such that each point can be described by a position vector r, such that it is r is described by two linearly independent vectors. These are called as primitive vectors, and then you have n1 and n2. These are integers, so you can uh, mm, should be able to describe any point within a lattice by such a translation vector, and if that's possible for a certain arrangement of points, it is called as a Bravais lattice. Um, so these two a1 and a2, these are linearly independent vectors. These are called as primitive vectors. For example, a1 can be along x-axis and 2 can be along y-axis, and these two would be linearly independent because ex and ey are linearly independent unit vectors. So what do we mean by this definition? Let's try to have a look at this arrangement and see whether it is a Bravais lattice or not. So how would we find out? Let's take a unit vector. Let's take a specific um, point within this um, lattice. Identify it as our origin, and then we draw our two unit vectors, or our two primitive vectors a1 and a2, like this. No, I want to define a certain, starting from here, I want to define the position of another point within the lattice, let's say this one. So how do I define it? I draw a vector starting from here to here. What would be that vector? You can define that vector as if you move by a single a1 distance along this direction and n2 distance along this direction by um, latest translation vector, which go from one point to another. So by the definition, you should be able to define such a translation vector for any point within the lattice, so that no point is missing here. Or in other words, you should be able to define such a vector for any values of n1 and n2, where n1 is the number of translation you move along a1, and n2 represents the number of translation you move along a2. It can be positive, it can be negative, but these are integer values, and a lattice, an Bravais lattice, should have all the possible n1 and n2 values in them. So this point would be, for example, 1 0. This point would be a 0 1, because I don't have to move along a1, but I have to move a unit by a2 to reach from the origin to this point. This is normally what n1 and n2 would mean, how many steps you move from the origin to reach that lattice point. So this point, by by this definition would be 1 1, and you can basically do the same procedure for any points within this lattice, and you would be able to cover all the points within the lattice uh, by using all the values of n1 and n2. So it's basically it this arrangement of point here is a Bravais lattice by definition given here. And uh, this should be an infinitely large object by definition, because it should be true for any value of n1 and n2. So it means that this lattice should be extended in all directions. But since this is a mathematical construction and nothing to do with real crystal, it's admissible over here. Uh, an equally valid definition of a Bravais lattice is like this: that you take any point in the lattice, um, such that the arrangement and orientation of the lattice around that point is exactly the same, no matter where you are in the lattice. What do I mean by this? Is, for example, if you take this lattice point, uh, you look at the lattice points arrangement around it and their orientation. So what do I mean by that is, let's say if you have this one, another point is towards right, exactly at a certain distance a1, the one another and one to the left of it, one to the bottom up on the upper side by a distance a2, and one to the lower side by a distance a2. This is how these 4 points are arranged at this point, at this lattice point. Now if I move to any other lattice point, let's say this one, I have exactly the same situation here. The orientation of the surrounding points is exactly the same, and the arrangement is exactly the same. So by definition, it is a Bravais lattice. And so this definition and the previous definition are exactly the same. So here I come to the so you should be able to label via this mm, representation any of the lattice points. The question is the choice of these two primitive vector for such a lattice, is it unique? So we have the same lattice, but let's define our primitive unit vectors in a slightly different way. So this is a1 as we had before, but a2 is defined in a different way. If you look at the xy coordinate or the Cartesian coordinate, you can define one way of defining these two primitive unit vectors would be in this way. So you can define now this point 1 0, it still can be labeled as 1 0, but this point, which is using the previous primitive unit vectors, one was 1 1, using this new primitive vector is just simply given by 0 1. And similarly you can label all the other uh, lattice points such that you can fill the whole lattice using these two primitive lattice vectors. So this would be a valid definition of primitive unit vectors as well. um, this is yet another choice for the primitive unit vectors, and you should check yourself. You should be able to label all the points within this lattice using these two primitive unit cells as well. Try to write the mathematical description of these two primitive unit vectors in S and X and Y coordinate system. Oh, let's take another kind of a lattice, which is usually called the triangular lattice. You can see these points are arranged in such a way. How can we define a unit vector or primitive unit vectors in this case? So imagine this is one of the coordinate origin. We take it at origin and we define two primitive unit vectors as a1 and a2, like that. Then this point can be described as a translation from origin by one along a1 and one along a2. uh, Similarly, you can label all the other points using this nomenclature using these two primitive unit vectors, and basically you can um, span all the points within, or you can describe all the points within this lattice using these two in the lattice. So this is basically this triangular lattice is a Bravais lattice. Uh, this is another choice for the primitive unit cell unit vectors, a1 along this direction and a2 along this direction. Um, uh, in this case, this point would then be 1 1, because you have to move a1 at this point, and then from here to here by a2 to reach this point from the origin. So that's why this is 1 1. This point would be simply 0 1. This point would be then move uh, two two times along a1 and one time along a2 to reach to 1, and in this way you can basically label all the points using these two primitive unit vectors as well. uh, to summarize the last points, if you have a Bravais lattice pattern, you can define primitive lattice vectors to describe each point within the lattice, and the choice of primitive lattice vector is not unique, so you can have different primitive unit vectors which you can define for a certain Bravais lattice pattern. So that's the summary of these last few slides. As an example, let's take another kind of lattice which is called as a honeycomb lattice, and it looks something like this, with points of the lattice arranged in a form of honeycomb. Uh, let's check if this is a Bravais lattice or not. So to check that, first we have to find or draw primitive unit vectors over here. So let's draw these two primitive unit vectors, a1 along this arm and a2 along that arm of the honeycomb, and see whether we can define or we can represent all the points of the lattice using these two primitive unit vectors. So you can imagine this point would be a 1 0 point, and this point would be a 0 1 point. What about this point, for example? To go to this point from the origin, you have to move -1 along a1 and +1 along a2 to reach this point. To see this point, you have to move 2 times along a1 to reach here, and then 1 time along a2 to reach this point. And similarly, you can label this point as 1 2. Okay, the question is, where is 1 1 point? So for 1 1 point, you have to move 1 unit along a1 and 1 unit along a2, so you would reach this point. So this is where your a1 1 should be. But is there a lattice point corresponding to a 1 1 combination? And the answer is no. So this lattice point is missing, and you can say that the honeycomb lattice is a non-Bravais lattice, because if it for it to be a Bravais lattice, you should have all the combination of the integers uh, within the lattice, which isn't fulfilled here. You can see this problem using the second definition of the Bravais lattice, which said that at each lattice point, the orientation and direction of the lattice point should be the same. So let's look at point B. So you can see that the arrangement is kind of a triangular. So you have 3 branches going out of P. one directly going up, one slanted to the left, one slanted to the right. What about point P? It is a lattice point, but if you move up, uh, there is no lattice point. If you move down, this is a lattice point, and you don't have lower left and lower right diagonal, rather you have upper right and upper left diagonals over here. So the arrangement at P is not equal to the arrangement at R, and that's why these two are not equivalent points, and hence for any lattice which have non-equivalent point, it's not a Bravais lattice. So honeycomb lattice. So we have seen these three different lattices, um, which fill up the whole space. So you can basically fill up the two-dimensional space, the whole two-dimensional space, with these three different lattices. Two of them turned out to be Bravais lattice and one turned out to be a non-Bravais lattice. The next question is, if you are working in two dimension and you want to fill the whole space with a lattice, or more specifically with a Bravais lattice, how many different unique combination of Bravais lattices in two dimensions are possible? And the answer to the question is that there are only 5 unique arrangement of Bravais lattices which are possible in two dimension. In other words, if you make any other Bravais lattice in two dimension, that Bravais lattice should be contained or should be describable by these 5 unique Bravais lattices in two dimension. So let's have a look at these. The simplest one is that of a square lattice, which has the two primitive unit vectors of equal magnitude and the angle between them is 90, giving you a square arrangement. If the magnitude of these two primitive unit vectors is different, gives you a rectangular unit cell. And if this rectangular unit cell has an added or an extra lattice point in the center, is called a centered rectangle. If the angle between the primitive unit vector is 120, is called a hexagonal, and if it is not equal to 90, then it is an oblique Bravais lattice in two dimensions. A related concept with the Bravais lattice is that of a unique unit cell. So a unit cell is defined as a region of space such that when you combine many identical unit spaces like that, it completely fills the whole space. Or in other words, it's kind of a repeating unit within a Bravais lattice. So the red points represent a certain Bravais lattice, and these, you can define unit cells, and of course to define unit cell you have to define primitive unit vectors, but a unit cell would be a region such that if you tile many unit cells together, then it completely fills the whole space. So you can see different unit cells, and all of them are valid unit cell for this Bravais lattice arrangement, because they are non-overlapping. These unit cells are not overlapping and they fill the whole space. Unit cells comes in two types: primitive unit cells and non-primitive unit cells. A primitive unit cell contains a single lattice point. So to see this, let's consider this lattice with these two unit cells defined in here. You can check that both these unit cells fill the whole space when they are tiled together. So they are unit cells in themselves. Let's concentrate on this first one, the unit cell S2. It contains two types of unit cells, two types of lattice points, the lattice points at the edges and a lattice point in the center. So how many lattice points does unit cell have? The lattice points at the edges, each point is shared with four other unit cells. So and because you have four such points, so in general you have 4 times 1 over 4, which means that the edges contribute in total one lattice point to this unit cell, and apart from that you have this extra lattice point in the middle. So in total you have two lattice points in this unit cell. In contrast, if you compare with this unit cell, the S1 unit cell, it contains only the points at the lattice point at the edges, and if you sum all of them up, it gives you one lattice point. So S1 is a primitive unit cell and S2 is a non-primitive unit cell. There's another way to define primitive unit cell, and they are called as Wigner-site cells. Wigner-site unit cell. So how do you define this unit cell? Um, let's say you have these lattice points and you start with a reference lattice point marked in black. So what you do is you connect this reference lattice point with the neighbor lattice point by a line, and then draw a bisector perpendicular to that connecting line. Then you do the same with the other neighboring point and draw a bisector, and you keep on doing it until you have exhausted all the neighboring points. The close structure which you get as the result of the connection of all these bisectors give you a Wigner-site cell. You might be wondering why I don't have a line to these lattice points. So if you draw a lattice point, a line connected this lattice point to your reference lattice point and draw a bisector, this bisector would be out of this unit cell, so that's why that's not important. Nevertheless, we have a way, a foolproof way of defining a unit cell, which is a primitive unit cell, and this unit cell is called a Wigner-site cell. So you can tile them together, and this way you can fill the whole space, and each cell would be a primitive unit cell this way. So to summarize the concept of unit cell, uh, here is the lattice, and we have defined three different types of unit cell. You have a primitive unit cell which contains only one lattice point. Another type of primitive unit cell which is formed by the bisector between neighboring lattice points. This is called as a Wigner-site unit cell. And another unit cell is called as a conventional unit cell, which tiles the whole lattice, but it contains more than one lattice point, and that's why it's a conventional unit cell and not a primitive. So something for you to check. Here we have various unit cells defined here, and you have to find out which one of them is a primitive unit cell and which one is a non-primitive unit cell. So try it yourself. Let's So until now we have been discussing lattice in 2 dimensions, but now extend this definition into 3 dimensions. So you have a combination of lattice points which extends into all three directions. So a Bravais lattice would be defined in such a way that if you start from a certain reference point, then you can define um, a translation vector in 3 dimensions now, such that a1, a2, a3, these are three primitive unit vectors defined in 3 dimensional space. And using these three primitive unit vector, you can define a translation vector which can take you from this lattice point to any other lattice point within this 3 dimension. As an example, this slide showed three different unit cells in three dimension. This is a simple cubic unit cell which has all the three sides of equal length, and the angle between all these sides is 90. If the two sides are same length but the third side has a different length, this is called a tetragonal unit cell. And if all the three sides are for different length, it's called an orthorhombic unit cell. As you can see, these all of these three unit cells, they have 8 lattice points at the edges, and you can imagine that each of those lattice points which are at the edges is shared between 8 different unit cells. So this particular unit cells contain only 1/8 of these particular lattice points. So in total, because there are 8 lattice points, which means that this is a primitive unit cell and contain only one. You can, apart from the primitive unit cell, you can have other combinations of unit cells as well in three dimension. um, so this is the primitive unit cell we have already seen. You can also have the case where you have lattice points on two opposing faces. These are called as single-sided face centered, or in other words, C-centered or AB centered. The primitive unit cell is called as represented by a letter P. If the primitive unit cell has an extra lattice point in the middle, as shown here, so you have this extra lattice point which sits exactly in the middle of the unit cell, this is called as eye-centering or body-centered unit cell. If you have lattice points at each of the six faces of this unit cell, this is called as face-centered unit cell, represented by a letter F. So these are the different centering which is possible: no centering, simple face centering, body centering, and face centered. The next question I'm going to ask is, since we have moved into three dimensions, what are the unique ways in three dimension in which you can fill up the whole three-dimensional space with Bravais lattices? Or in other words, how many different unique Bravais lattices you can define in three? The answer to this question is that there are 14 Bravais lattices in three dimensions which can be uniquely defined. So the unit cells of these 14 unique Bravais lattices in three dimensions are shown here in this table. These 14 unit cells can be further classified into 7 crystal systems, as shown by the names here. For example, you can have monoclinic, triclinic, orthorhombic, tetragonal, hexagonal, trigonal, or cubic crystal systems. This classification of these unique Bravais lattices into crystal systems is based on symmetry considerations, which we would study in a minute. But before going into that, I would like to emphasize this point that these unique identification of unique Bravais lattices in three dimension is a mathematical exercise, and this has not to do specifically with what physical crystals are available in nature. For example, if you look here, in these one, you can find uh, structure with 4 corners or structure with 6 corners, but you won't find structures with 5 corners or 7 corners. And you can mathematically show that a pentagon or a heptagon won't fill the three-dimensional space, and you would have gaps left behind. So these are mathematically possible 14 Bravais lattices in three dimensions. Now coming to the point of how we do this classification based on symmetry considerations. So for that, I would like to first introduce the various symmetries which can be found in three-dimensional unit cells, which we defined for previously for the three-dimensional Bravais lattices. Some of these symmetries operations are the following. For example, if you take a tetragonal system like this, a tetragonal unit cell, and consider an axis of rotation which passes through its center, you can rotate this tetragonal unit cell by 180 degree, and the resulting structure would be indistinguishable from what you started with. Such an operation is called as a twofold rotation operation, and this axis of rotation is called as twofold axis of rotation. Why it's called twofold axis of rotation is because if you start with a lattice point in one corner, and if you do two such operation, that corner or that lattice point would come back to its original position with which it started. So that's why you would have this is called as a twofold rotation operation. You can similarly think of threefold rotation, which would be 120-degree rotation, or fourfold rotation axis, which would be 90-degree rotation. So if a structure is rotated by 90 degree and remain indistinguishable, it would contain a fourfold axis of rotation represented by C4 then instead of a C2, which is mentioned here. Another operation is that of a symmetry operation, that of a reflection or mirror of symmetry operation. So consider this cubic unit cell and consider a plane passing exactly through the center, shown here. If you reflect the right side, you get exactly the left side, and if you reflect the left side, you get exactly the right hand side, if the reflection occurs via this plane which is shown here. Such an operation is called as a mirror symmetry operation, and it is defined by this letter sigma. Another important symmetry operation is called a center of inversion. So certain unit cells, they contain a certain center such that if you invert one lattice point by the center, you get another, you get to an identical lattice point in the unit cell. Just like if you consider an S or a Z, this edge, if you invert it by this center, you get to this edge, which is basically an inverted side of a version of this side, or a Z on this edge is inverted to a Z on this edge. So this is called as center of inversion operation, or a symmetry of center of inversion represented by a letter I. Then you have this mixed symmetry operation which involves both rotation and inversion. So first you take, for example, you take such a structure with these four lattice points. Uh, if you rotate, let's say 1 3 about an axis of rotation which passes through its center by a 90 degree, you have these configuration. And if you invert these two lattice point via its center, you get these 2 points, which is exactly what you have here. So what you get after such a combination of these rotation and inversion is a configuration which is similar to what you started with. These are called as point symmetries because when you do these operations, there is at least one point which remains unchanged. And for example, here, this point which is in the center, it would remain unchanged by a symmetry operation. Similarly, a point which is in the center here, it would remain untouched until by reflection or by rotation. So that's why these are called as point symmetry operations. Now, as I showed earlier, that the classifications of crystal classes is done uh, using the symmetry consideration. So the idea for that is that we have these 7 different crystal classes, and they are defined or classified in this way because each of them has a characteristic symmetry element in them. For example, a cubic system is a cubic because it would contain threefold rotational axes, and it would contain four such threefold rotation axes. So any structure which has four times threefold rotation axes, or C3 rotations, would be called as a cubic structure, and so on and so forth. So this table contains all the symmetry, the characteristic symmetry elements, uh, which these different classes contain. One point to note, for example, a cube, it would not only have this threefold axis of rotation, this is the characteristic symmetry element, but it would also contain other symmetry elements like reflection, or fourfold rotation, or twofold rotation. But only this threefold rotation axis, and four of them, this is only unique to a cubic crystal system. So this is an important point to note here. Now coming back to this list of unique Bravais lattices in 3 dimensions, let's have a look. Uh, you can have a cubic system which contains these 3 unit cells. Uh, in a cubic system, all the 3 sides are of the same length, and the angles of the 3 angles are 90 degrees. The angles between the A, B, and C sides are 90 degrees. Then you have tetragonal system. Again, the angles are 90 degrees, but what you have is uh, 2 sides are of similar length, and the third side is of a different length. And here you can have a primitive unit cell or a body-centered unit cell for a tetragonal system. Then you have orthorhombic system. In orthorhombic system, what you have is a unit cell with A, B, and C of different lengths. The angles are still 90, and you can have a primitive, a body-centered, a side-centered, and a face-centered. Uh, the side-centered is also called as base-centered sometimes, so, or C-centering, in other words. You have some other structure like a triclinic structure in which all the 3 sides are of different length, and the angles are neither, all the 3 angles are not 90 degrees, so which is a completely, this is a structure with the least symmetric structure in all of these 14 Bravais lattices. And you have the rest as well. So please have a look at these. For example, hexagonal structure. So there's a hexagon and the hexagonal structure, but the hexagonal unit cell is defined via this unit cell within this hexagon, this big hexagon unit cell. So this unit cell, which is a primitive unit cell made out of this big hexagon, is called a hexagon primitive unit cell. and the angle between A and B side is 120 degrees. You can have extra lattice points within a hexagonal um, big unit cell, and when you do that you can define another type of unit cell or primitive unit cell which is called a trigonal unit cell in here. Then you have a monoclinic system in which all the three sides are again not equal to each other in length. Uh, the two angles are 90-degree and the third angle is not a 90-degree. So this last table showed that for a tetragonal system, we have only two entries in there. One is a primitive tetragonal and the other is eye-centered tetragonal, but face-centered tetragonal and C-centered tetragonal unit cells are missing in there. And now we would like to discuss why is that the case. So consider this tetragonal unit cell. So it's a tetragonal unit cell with C centering. So that's if you consider, in which case these two sides are of the same length and this side is of a different length. The angles are 90 degrees here. And C center would mean that this you have only these two lattice points on this face and this face. And here we have shown our two neighboring C-centered tetragonal unit cells. You can, if you do this, you can define another tetragonal unit cell denoted here by this dashed line. And that tetragonal unit cell is a primitive unit cell. So what does it tells you? That if you have a if you have C-centered tetragonal unit cell, you can make P primitive tetragonal unit cells out of them. So it means that C-centered system is not a unique system and that's why it's missing from the previous table. Similarly, if we take an F-centered tetragonal unit system which is missing previously, so this is the big cell is the face-centered tetragonal unit cell. You can make this unit cell out of them, out of this unit cell, so that because there is one which is a eye-centered unit cell, because there is one atom or lattice point in the center over here. So you can make this is, so this new unit cell here is the eye-centered unit cell, which means that if you have F-centered tetragonal unit cell, you can make eye-centered tetragonal unit cell out of them. So that's why the F-centered tetragonal unit cell is missing from the last table. So let's have a look at a few important unit cells, uh, particularly cubic cells. So I will start with body-centered cubic cell, normally represented by a BCC unit cell, as shown here. So in XYZ, you can define your primitive unit lattice vectors, A1 along x-axis, A2 along y-axis, and A3 along z-axis, all three with the same um, magnitude. And this would define your the volume of your unit cell, which contains 8 lattice points at the edges and one lattice point exactly in the center. You can represent the same unit cell in a different notation, which is normally called a planar view. So if you look at this unit cell from the top, you can see like an atoms lattice points at either at the height 0 or at height a, which are represented by these four lattice points, and you have one lattice point in the middle which is at a height a by 2 if you start 0 from the lower plane. uh, for 0 or a, we don't normally denote it, so that's why these edges ones lattice points are left unmarked, but the center one, because it is at a height a by 2, it is then we mark it as a by 2 as such. Now, the next question is, how many lattice points are there in total in this unit cell? So the lattice points, if you consider the edge lattice points, each lattice point here is shared between eight unit cells. So 1/8 part of this particular lattice point is inside this unit cell. The rest of them are in the neighboring unit cells. So uh, 1/8, 1/8, 1/8, 8 times 1/8, it would give you one lattice point for all the lattice point at the edges within the unit cell. Then you have this internal point which is in the center. It is entirely inside, enclosing this unit cell, so you would just add this one into here as well. So it gives you the total number of lattice point is 2 in the body centered unit cell. So how to mathematically describe our body centered unit cell? So by convention, you need to define only two lattice points to describe a full BCC unit cell. You need a corner one. So let's say this is the corner one, which is because I have defined my coordinate in such a way that this is my origin. So this origin of the unit cell would be represented by n1, n2, n3. So for example, my coordinate origin was somewhere else, but that was at a lattice point. So this lattice point would be n1, n2, n3 coordinate points away from the original origin which I have defined. So this is my one lattice point, and that lattice point can be defined as n1, n2, n3 plus 0, 0, 0, because this lattice point is exactly at the reference point of this unit cell. The other lattice point you need to define is the centered one. So it is uh, a half, a half, a half away from your reference point of the unit cell. So the coordinate of the reference point is n1, n2, n3, plus you add a half, a half, a half, and you get to represent the position of this lattice point within a BCC unit cell. You may ask why I'm not. So these are the only two lattice points which you need to define your whole BCC unit cell. You might ask why I'm not writing a coordinate for this lattice point or this lattice point. So the answer to that is that this lattice point will be the reference point for the unit cell which is above this unit cell. So this would be the 0, 0, 0 for the unit cell which is above it. Similarly, this would be the unit cell which would be on the upper right corner of this unit cell. This lattice point would be the reference point of the unit cell which is exactly to the right of this unit cell. So all the other lattice points at the edges, they belongs to the other unit cell. This unit cell, this particular unit cell, has one full lattice point, edge lattice point, this one as a description, and the one which is in the center, the rest by convention belongs to the neighboring lattice points. And this is true as well because we have only two lattice points, two whole lattice points in the unit cell, and that's why a description, mathematical description of just two lattice points, one at the corner, at the reference corner, and one at the center, should be enough. So you might ask that, okay, I have defined this unit cell, but this unit cell is not a primitive unit cell because it contains two lattice points, and by definition a primitive unit cell contain only one lattice point. So the next question which arises, can I define a primitive unit cell in a BCC crystal or a BCC lattice system? And the answer is yes, you can. If you define uh, your lattice primitive lattice vectors not like this but rather like this, so you have a1 along x-axis, ay along y-axis, and a3 in a diagonal between x, y, and z, which is a half, a half, a half. So if you define a unit cell using these a1, a2, a3 defined in this unit cell, you would get a unit cell as drawn in red color over here. And this would, by definition, contain only one lattice point, because only lattice point it would have at the edges of this red unit cell. That's why this would be a primitive unit cell. So these are the primitive unit vector of a primitive unit cell of a BCC lattice system. So the next question you might ask is it the only way you can define a primitive unit cell in a body-centered cubic system? And the answer is no. For example, if you consider these three adjacent unit cells, the conventional unit cell. So now I can differentiate between this red unit cell and this black unit cell. This is your conventional unit cell defined by these three axes, these three orthogonal axes, and this is a primitive unit cell defined by these three these three primitive unit vectors, which are non-orthogonal. So if I have three conventional unit cells like this joined together, uh, let me represent, or let me define three primitive lattice vectors, a a1, a2, a3. Like in that case, like that, you get a unit cell like this. This is again by definition a primitive unit cell with uh, lattice vectors defined in this way as shown here. So it's another choice of primitive unit cell in uh, body-centered cubic system. So you not only have one choice of primitive unit cell, you have another choice of primitive unit cell. Normally this second definition of primitive unit cell is preferred because you can see that mathematics is more symmetric as compared to this one. We also defined a way to describe a primitive unit vectors via a Wigner-Seid method. So can we define a Wigner-Seid unit cell for the case of a BCC system? And the answer is yes, and the resulting Wigner-Seid cell for a BCC looks something like this. So what we have is a lattice point in the center. You connect that the center lattice point to the one at the edges, for example via this line, and then you bisect it by a plane, and similar you do with this one and that one and all the edges. You can also combine the one which is in the center uh, here with the one which is in the center above, and that would give you a bisector plane like this. Okay, so these are all bisector planes of the lines which connect the central atom in a body-centered cubic to the neighboring atom, and this close shape is the Wigner-Seid cell of a body-centered cubic system. So we have either you can define a primitive unit cell like a Wigner-Seid cell, or you can define a primitive unit cell like this in a BCC system. Now coming to another cubic system, which is the face-centered cubic system. Again, we have this conventional unit cell defined by these three primitive unit vectors defined along x, y, and z axes, all three with the same magnitudes. So you can define this unit cell, or you can represent this unit cell in planar view via such a description. So you have the edges atom, which can be either at a height 0 or at a height e, and uh, both. So we don't write any description for these, because if you don't write anything here, it means that either it is 0 or a. But you have this atom, for example. This atom is at point A, which is here. Again, you don't write anything for this one, because uh, it is the same as the one at the edges. You can have exactly another lattice point below this centered one, and so this point would represent again either a 0 or an A, so that's why they remain unlabeled. But if you look at this lattice point, which is represented by this point in the top view, or this lattice point, which is represented by this in the top view, uh, these are at a height a by 2, and similarly you would have these other two lattice points at a height a by 2, and since these are not at either 0 or a, we represent them by a by 2, a by 2, a by 2. So this would be a description of such a unit cell in a planar view. The next question is how many lattice points are here. So again, for the edges, you have 8 edge lattice points, and because you have 8 edges, each one contribute 1/8 to this unit cell. So you had 8 into 1 over 8, you have in total 1 lattice point eh, from the edges, or rather the corners. Then if you look at the faces, these faces, so this lattice point, for example, this lattice point is shared uh, between this unit cell and the unit cell which is just above it. Similarly, this is shared between this unit cell and the one which is towards its right. So these lattice points, which are on the faces of the cubic unit cell, they only half of them lie within this conventional unit cell. So you have 1/2, and because you have 6 of them, so the total lattice points contributing from the faces are 6 multiplied by 1/2, which gives you 3 lattice points, 1 from the corners, and in total you have 4 lattice points in this cubic conventional unit cell. So to describe this unit cell, you need to identify 4 lattice points mathematically, which are shown here. So you take this as the reference of your unit cell, and that reference would be represented by n1, n2, n3, uh, starting from a certain origin of a coordinate system. So if this is the reference point, then this point, which is at exactly at the reference, is represented by n1, n2, a3 plus 0, 0, 0. Then you need to define the ones at the faces. So you can define, for example, you can start with this point on the face. So you have this reference point, then you go a half, and then a half, half along x-axis, half along y-axis, and you would have, or half along a1 and half along a2, and so that's why this would be represented by n1 and 2, which is the reference lattice point, plus a half, and a 0. Similarly, this one would be represented by going 0 along a1, half along a2, and half along a3. So this would be this one, and the other one would be this lattice point in the face, so that you go half along a1 and half along a3. So that would be a half, 0, and a half. Now again you might ask, what about the other lattice point? I don't need to define mathematically the rest of the lattice point because they would belong to the neighboring atom. So you only need to define this lattice point and these three uh, lattice point on the faces to fully describe a face centered unit cell. The next question is, can we define a primitive unit cell for a face-centered cubic system? And the answer is yes, you can. If you define your A1, A2, A3 primitive unit vectors in this way, so that A1, for example, it starts from the reference point and it ends on the lattice point which is at the on this face, at the center of this face. Then you can, for A2, you can start from, let's say, the reference point and it points toward the lattice point which is in the center of this face, and similarly A3 would be the one which is in the center of this face. So mathematically you can write them as A1, A2, A3 given by a half along y and z, a half along x and z, a half along x and y, and so on. So the shaded region here is your primitive unit cell in an FCC, and it would have a volume 1/4 of the conventional unit cell, which you can prove. So one can define a Wigner-side cell for a face-centered cubic unit cell as well, and it looks something like this, uh, where it has this closed shape which you see here is the Wigner-side cell for an FCC unit cell or FCC crystal. If it's hard to imagine what's the atom in the middle is, it's basically the atom at the face of the conventional unit cell, which makes up this. As an aside, I would like to discuss an important property of lattices, which is a coordination number. So it is something related to the number of neighbors surrounding a certain lattice point. So for example, if I consider a cubic lattice and I imagine a certain lattice point within a cubic system, and then I ask a question, what are the number of nearest neighbors of this lattice point within a cubic system? So if you consider this as your central lattice point, then the number of nearest neighbors are represented by these numbers, these highlighted points. All of these points are at a distance a away from it. If you consider any other point, for example, this point, this is and the distance under root 2a from your assumed point. So this would be not the nearest neighbors, but the next nearest neighbors, and so on. This, for example, this would be the next nearest neighbor. So the coordination number is a number defined for a certain lattice, and the coordination number represent the number of nearest neighbors for a particular lattice structure. In the case of a cubic crystal, it is the coordination number is 6. You can similarly define a coordination number for example, a BCC crystal or a body-centered cubic system. For example, these are a combination of like 8 BCC unit cells, and if you take this black one as your reference lattice point, and then you ask the question, how many nearest neighbors does this lattice point has? So the nearest lattice points are the red ones, which are at a distance a by 2 away from it. So the red, all these red, you would have 8 such red points, so it means that this crystal has 8 nearest, this lattice point has 8 nearest neighbors. The next nearest neighbors are the greens ones which are shown here, so these are distance a away from it, so the which would include this lattice point, this lattice point, this one, the one here, and the one here, which in totals become six. So six next nearest neighbors. The second next nearest neighbors are then given by the blue ones. So you have the blue ones which are here, 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 these two, one here, and one here. So in total 12 second nearest neighbor, and so on and so forth. So there's an important number which a coordination number is an important number which characterize a certain lattice. So to summarize, in this lecture, we have introduced the concept of Bravais lattice and different aspects of a Bravais lattice. For example, what are lattice vectors? How do we define a unit cell? What is the difference between primitive and non-primitive unit cells and Wigner side cell? Then we have also try to answer the questions how many unique Bravais lattices you can define in 2 and 3 dimensions, and how do you classify them with respect to the symmetry operation. Um, and we have looked into examples of cubic crystal system and discussed what are the conventional, how to define a conventional primitive, a Wigner site unit cell for cubic crystal systems. So the lattice or Bravais lattice is a mathematical construction, and it basically tells you in how many unique ways you can fill up the space with patterns of points. We haven't discussed yet about atoms or real crystals, which this is something which we would take up in the next lecture.